Welcome to part 2 of a 6-part series where we will explore using the Intel Quartus Prime Pro software. In part 2 of this series, I will introduce the various design entry methods including system design and simulation, as well as using the Intel Quartus software settings and assignments. I will first go over the variety of design entry methods supported in the Intel Quartus software. The top-level file and all the supporting files can be in any of these formats. As for other design files in the hierarchy, the Intel Quartus Prime software allows you to mix and match between any file types you want. For example, you could instantiate a VHDL entity in a Verilog module, as long as the instantiation syntax and port mapping are correct. This gives you the flexibility to enter the pieces of your design in any format you choose, knowing that they can all be used together. Intel Quartus Prime software includes a full-featured schematic design editor. With the schematic design editor, you can create your design from standard design blocks such as gates, flip-flops, and I/O pins. You can also quickly and easily instantiate IP in your design. Once you place all your logic, simply connect the blocks together using wires and buses. While most new designs are created in HEL instead of schematics, a schematic is often helpful as the top-level design entity as an easy way of creating simple test designs to understand the functionality of an Intel FPGA IP, or as a block diagram for connecting pieces of a large design together. You can convert schematics into HEL code for use in other projects, or create black box symbol files out of HEL files for instantiating those designs in a schematic file. The Intel Quartus Prime software supports all versions of VHDL and Verilog. For synthesizing HEL design files, you can use Intel Quartus Prime software integrated synthesis, or any third-party synthesis tool. If you are not entirely familiar with HEL commands, use the built-in help resources in the text editor to get more information. When writing your HEL, it is always good to recognize the architecture that you are targeting. The synthesis tools in general do a great job optimizing your HEL design to fit into the logic resources that are available in Intel FPGA devices. Here I have a screenshot of the resource property viewer showing the inferred logic outlined in blue. This screenshot is of an adaptive logic module, often referred to as an ALM. ALMs will have registers, carry logic which has fast, dedicated connections to facilitate optimal arithmetic functions, and number of lookup tables. In this diagram, you can make out 6 lookup tables which are all being used. The LUT in an ALM is an adaptive LUT, or a LUT. An a LUT is similar to a LUT, but it can be split and configured into different sized LUTs to accommodate 2 separate functions of any type, from the very simple to the very complex. All 8 inputs can be used to perform complicated arithmetic functions, but the A-LUT can be split in different ways for simpler functions, such as 2 LUTs with 5 and 3 inputs each. A 5-input LUT and a 4-input LUT, where the second LUT shares an input from the other LUT. 2 5-input LUTs where the second LUT shares 2 inputs from the other LUT. Or a 6, 7, or 8-input LUT. However, the software tools do a great job inferring the resources from your HEL code, so you rarely need to concern yourself about the inference results. The Resource Property Viewer is an excellent tool to see how logic is configured based on your HEL code. What I have here is Verilog code, and the resulting resources that get inferred from the Verilog. As I comment out sections of my Verilog code, you can see different resources being inferred as a result. As I remove some of the control structure from my inferred register, that control structure does not get used in the final results. However, I still use the same register in the FPGA, and those resources don't get used if I need them. If you are uncertain as to what types of resources you can infer or what your coding structure needs to look like to infer the resources, the built-in text editor has template examples that you can utilize to get you going. The examples include both VHDL and Verilog. Another way of creating a design is through the use of IP cores. IP cores are pre-made design blocks you create and customize in the Intel Quartus Prime software. IP can represent anything from simple logic, like gates and flip-flops, to more complicated structures such as PLLs or DDR memory controllers. Many IP cores are free and installed with all editions of the software. They are easy to create and easy to change if necessary. Simply drop them into your existing design to speed up the design entry process. All IP cores included in the Intel Quartus Prime software are also pre-optimized for Intel FPGA devices, so they can take advantage of device-specific features. There are 2 main types of IP cores in the Intel Quartus Prime software base suite and Intel FPGA IP. The IP base suite is a set of IP cores installed with all editions of the Intel Quartus Prime software. Light edition users require a license for the base suite. However, the IP can still be used through the Intel FPGA IP evaluation mode feature, discussed in a moment. You are free to examine and edit the files generated for these cores. HDL simulation models are provided for simulation of the IP base suite cores in third-party simulation tools. A general list of the cores found in the IP base suite is shown here. To learn more about what's included and get more details on the individual IP cores, click the link to go to the IP base suite information page on the Intel FPGA website. The second type of IP cores are the Intel FPGA IP. Unlike the base suite IP, Intel FPGA IPs are generated as encrypted files, so they cannot be viewed or edited. They require a purchased license for their use in a production design. These IP cores are typically more complicated, high-performance logic functions. There are two types: IP that are created by Intel FPGA and either included in the software or available for download from the Intel FPGA website, and cores created by partners of the Intel FPGA IP Core Partner Program. If you are interested in using a partner-created IP, contact the vendor instead of Intel for information and support. A useful feature available with all Intel FPGA IP and some partner IP is Intel FPGA IP Evaluation Mode. The Intel FPGA IP Evaluation Mode feature lets you proceed through the entire design process without having to purchase a license. You can simulate the IP using the included simulation models, and even program a target FPGA device with the design. The only caveat is that the programming files generated are time-limited and require an active JTAG connection to the board. This means that without a license, the program design will stop working after about an hour. For more information about the Intel FPGA IP Evaluation Mode feature, see Application Note 320 on the Intel FPGA website, linked here. Here are just a few examples of the Intel FPGA IP that are available. There are, of course, many more. See the Intel FPGA website link for a full searchable list. For more information about any IP core, see the documentation available for that core on the Intel FPGA website. The IP settings, available in the Intel Quartus Prime Options dialog, provide some options for how IP gets generated and used. Normally, when generating IP, you can choose the output HDL you want to use for the core. One setting to be sure that is checked is generating simulation models of your IP. With this option set, you will be easily able to simulate the IP that you have instantiated in your design. If you'd like third-party IP or your own custom IP to be accessible through the IP catalog, add search paths to the IP here in the IP catalog search location settings. You can add global paths so that all projects can see the IP or set project-specific paths. Search paths set here are also used by the IP catalog in the Platform Designer System Design tool. There are a number of other tools you can use to enter your design into the Intel Quartus Prime software. Another tool available is the State Machine Editor. The State Machine Editor is a graphical tool that lets you easily create state machines by adding inputs, outputs, states, and state transitions to a schematic. You can manually add state machine elements or use the State Machine wizard from the Tools menu or toolbar to automatically create state machines based on input criteria. You can edit any already created element by double-clicking. The state machine created in the State Machine Editor is saved in a .sesmf file, which you create from the File menu or the Tasks window. To include the state machine in your design, you cannot simply add the .sesmf file to your project. You must click Generate HDL to create an HDL output file. When you click Generate HDL, you select whether the output should be Verilog or VHDL. The code generated by the State Machine Editor is optimized for Intel FPGA devices. Simply add the generated output file to your project or copy and paste it into an existing design file. The output HDL file must be generated to use the state machine in your design. If you have any RAM or ROM memory blocks in your design, you may want to initialize their contents for simulation or for production. You can do this with a memory initialization file. You can create two types of memory initialization files in the software: the Intel standard .hex file and the Intel FPGA.mif file. Either can be used to initialize RAMs or ROMs in an Intel FPGA design. This initialization occurs after device reset and programming, but before the design itself comes out of reset. All memory blocks in the device power up low, but programming with an initialization file changes the contents of the now powered-up memory blocks to match the values in the file. Using an initialization file will increase the size of programming files generated by the Intel Quartus Prime software assembler, the compiler module responsible for generating these files. Once you created a memory initialization file, you must associate the file with a RAM or ROM in the design. If the memory is created in the IP parameter editor, turn on the option to use memory content data on the MEMINIT tab of the parameter settings. Type in or browse for the file. If you created the memory directly in your HDL code, use the RAM init file synthesis attribute with the memory file to associate the memory contents. As mentioned earlier, the file you create for eventually programming your device will increase in size by the size of the memory, since the memory initialization file must be included with the programming data. If you use an onboard flash memory or some other device to program your FPGA, the programming device must have enough storage space to accommodate the increased size of the programming file. Another method of design entry in the Intel Quartus Prime software is through the use of third-party tools. The Intel Quartus Prime software can work with any tool that generates an EDIF netlist or any netlist written in VHDL or Verilog formats. This includes the VQN format generated by some tools. To include these designs in a software project, simply specify the tool used to generate the files, instantiate the black box blocks into your design, and add the files to the project. As an example of when you might do this, some third-party tools can be used as a replacement for the built-in Intel Quartus Prime software synthesis process. The third-party tool may provide more options or generate better results than the Intel Quartus Prime software built-in synthesis. This list shows the vendors and the tools that Intel FPGA actively works with to provide up-to-date information on Intel FPGA devices, ensuring highly optimized, device-specific synthesized logic. I will next go over the system design entry method supported in the Intel Quartus software. Platform Designer simplifies complex system design by raising the level of abstraction during system development. Instead of designing at the signal level, Platform Designer allows a designer to design at the system component level. Platform Designer provides a standard platform to integrate off-the-shelf IP cores and your own custom logic. It enables design reuse by allowing you to create your own custom IP cores that can be reused in other designs. Platform Designer scales easily by allowing a hierarchical approach to system design. The end result is a faster time to market by reducing development time, reducing the number of errors when connecting the system together, and simplifying the verification process. System design can be a difficult process. Here is an example of a typical system. You have different components in your system that have different interfaces that need to communicate in order for the system to work. Designing custom interface or glue logic to enable this communication, along with things like arbitration and width matching, requires a lot of engineering effort. This type of logic does not add a lot of value, but it is necessary to get the system connected. Putting this together is a naturally error-prone process as the designer has to resolve the various data, control, and status signals between the different interfaces, as well as the timing of these signals. When you use Platform Designer to design your system, Platform Designer generates a custom-built interconnect structure that facilitates communication between all of your system components. Again, this abstracts away from the designer the manual process of manipulating interconnects and signals, and allows them to instead focus on integrating system blocks. Here are two host devices talking to two agent devices. The green devices use Avalon memory mapped interfaces, and the blue use another interface like AXI. With the Platform Designer interconnect between them, any host can communicate with any agent, so the designer only has to add the components to the system and begin data transfers. Here's what the Platform Designer tool looks like. Components, which can be off-the-shelf IP cores or your own custom IP, are added to the system using the IP catalog, similar to the IP catalog found in the main Intel Quartus Prime software. The added components are listed in the System Contents tab. The system is built by simply connecting the interfaces of components together. Platform Designer uses standard interfaces, like Intel's own Avalon interface and ARM's AXI interface, to guarantee compatibility and connectivity between components. The tool features a hierarchical view to easily explore the system and a number of completely customizable tabs that provide different views of important system information and configurable options. Once the system is built, HDL code is generated in a similar manner to how IP cores are created through the IP parameter editor. DSP Builder for Intel FPGA is made up of standard and advanced block sets. Through the MATLAB Simulink environment, you can use these block sets to create high-performance HEL code for DSP applications. Simply build your DSP algorithm in MATLAB and generate the code for use in the Intel Quartus Prime software. oneAPI is an open cross-industry, standards-based, unified, multi-architecture, multi-vendor programming model that delivers a common developer experience across accelerator architectures for faster application performance. The Intel FPGA add-on for oneAPI-based toolkit is a specialized component for programming these reconfigurable devices. When paired with the Intel oneAPI compiler, the FPGA add-on allows developers to compile an FPGA bit string, configuring these flexible platforms to meet a broad range of application needs. Data parallel C++ functions, called kernels, get compiled offline into a partial bit string with hooks in place so that the newly created module, also called a custom compute pipeline, can be downloaded into an already existing infrastructure running in the FPGA. The kernel is downloaded when the host running the entirety of the program comes across the function that is intended for the FPGA. In this manner, the host offloads the work that the main CPU would have had to do to the FPGA that is residing in an accelerator card, which is in turn plugged into an interface like a PCIe slot. I will next go over simulating your design in the Intel Quartus software. Here are the steps to run through a simulation of your design. The first thing is to make sure you have a test bench ready to go. The test bench has to be of your own making and can be included as one of your source files in your Intel Quartus software project. Just be sure that the test bench is not marked as your top-level entity, as the software uses the top-level entity information to synthesize and fit your design. Next, be sure to double-check in the IP settings that you have selected to generate simulation files for the IP that exist in your design. Also, when generating your IP in the IP parameter editor, be sure to select the HEL language if your choice in the simulation section of the HEL generation window. In this step, you go to the Tools pull-down menu in the Intel Quartus software and select Generate Simulator Setup Script for IP. This action will generate the necessary simulation files for your IP along with a template that you can use. Create your own Questa-do file. Open the newly created tickle script found in the project/mentor directory and copy and paste from the begin and end into your newly created do file. With your new do file in place, you will need to add commands so that your project source files also get compiled. Having some familiarity with the Questa simulator and its commands will be helpful. The only thing that is left to do now that your do file is created is to launch Questa and change directories to where your do file is located and run the do file. Finally, I will go over settings and assignments. To control many aspects of the way synthesis and place and route are performed on your design, you use project settings and assignments. Both are accessed from the assignments menu or the tasks window. Settings are project-wide switches that affect everything in your design. Examples of project settings include the selection of the target device and the version of Verilog or VHDL used for input design entry files. Assignments are settings that are applied to individual entities or nodes in the design. Examples of assignments include the selection of I/O locations for signal nodes and the enabling or disabling of certain device features. All settings and assignments, except for timing constraints, are stored in the project's QSF file. Here are the categories found in the main settings dialog box. Select a category from the list and make settings changes on the right side of the dialog box. Some examples of settings you can make are the selection of the top-level design entity, files that should be added or removed from the project, project libraries, and VHDL and Verilog version selection. You can also edit settings for EDA tools, timing analysis, general compiler options, as well as other synthesis and fitter options. As an example of some of the many settings available in the settings dialog box, the Intel Quartus Prime software includes a number of general optimization settings. These are used to adjust how the compiler works in order to meet your design goals, such as improving design performance or reducing overall power usage. These options are found in the compiler settings category. You can select a general optimization mode, or click the advanced settings buttons for either synthesis or the fitter to enable, disable, or change different optimizations performed by that stage of the compiler. The QSF file is included with every project. The QSF file stores all the settings and assignments you create for your project in a tickle syntax. Any setting or assignment created in the Intel Quartus Prime software GUI is stored here. If you want to, you can manually edit the QSF file instead of using the GUI. However, it is recommended that you quit the GUI before editing the QSF file because of conflicting assignments between the GUI and the manually edited QSF file. You can organize the QSF file by categories using a command from the project menu. You can add comments or white space. New assignments created by the GUI are placed at the end of the file. If you don't want to directly edit the QSF file, you can create a separate Tcl script and source it from the QSF file. For example, the QSF file here sources a Tcl file named location assignments, which contains all the I/O location assignments for the project. If you want more information about editing the QSF file and the syntax used, check out the Intel Quartus software settings file reference manual, linked here. With all these files created and used by the Intel Quartus Prime software, it's important to understand the priority with which the software uses the assignments and settings contained in these files. Higher priority settings are used, while identical lower priority settings are ignored. The software always looks at the QSF file first. It will then look at a revision-specific QBF file located in the project directory. These files are automatically generated when you open a project with more than one revision and a version of the Intel Quartus software different from the one in which the project was created. We'll talk more about revisions in a little bit. The software next looks at a local PDF file in the project directory that you may have created with a copy of the main QBF, or if you performed a project archive and restore. Finally, the software looks at the main QDF file located in the Intel Quartus Prime software installation directory. The next project management feature is project revisions. With revisions, you can explore new sets of constraints or compile options without affecting any current settings or your design files. Creating a new revision creates a new QSF file with the changed settings, such as a different target device or different synthesis or fitter options. You can easily switch back to the original settings if desired. When you create a new revision, revision-specific files are created in the project directory. The next time you compile the new revision, revision-specific compilation database files are added to the QBD folder. You use the revisions dialog box, accessed from the project menu or the tasks window, to create and manage all project revisions. The current revision is indicated by a green checkmark in the revision list. Select a revision and click Set Current to set the selected revision as the current revision to work with. Double-click the new revision cell to create a new revision. New revisions can be created from scratch or based on existing revisions. A text description can be included as a reminder about what is included or changed in the new revision. When creating a new revision, you can choose to set the new revision as the current revision or continue working with the original revision. Click OK to create the new revision. As mentioned, when you create a new revision of the project, a new QSF file is created with the name of the new revision. All active revision names are stored in the QPF file, as shown earlier, to keep track of them. When a revision is created, a text file is also created in the project directory. This file includes the text description of the new revision input in the Create Revision dialog box. You can switch between revisions of the project in the Revisions dialog box, or with the pop-up menu in the Intel Quartus Prime Design software toolbar. Selecting a different revision from the pop-up list or the Revisions window immediately adjusts all settings and assignments to that revision. Now let's take a look at assignments. Remember that assignments are applied to individual design entities or nodes. We'll look at the assignment editor, the main tool for creating and editing assignments. We'll look at some example assignments and then, in the next section, focus on I/O assignments and the tools available to work with them. Before you can create an assignment, analysis, and elaboration, the first step of the compilation process must be performed. This process establishes the design hierarchy and the node database, so be sure to run it from the Start submenu in the Processing menu to begin creating assignments. The Assignment Editor, accessed through the Assignments menu, the toolbar, or the Tasks window, is the main tool used to create and edit assignments. The Assignment Editor organizes assignments in a spreadsheet-like format. Many familiar spreadsheet operations are available in the Assignment Editor, such as sorting on columns, copying and pasting, and cell autofill. Assignments consist of a few basic pieces of information. This includes the node or entity the assignment acts upon, the type of assignment, and the value of the assignment. You can also disable individual assignments instead of completely removing them to avoid re-entering them later. But to create a new assignment without cross-probing, you have to locate the correct node or entity and enter it into the From or To column. To do this, double-click a cell to type in node or entity information directly or click the button indicated to open the Node Finder. For the From and To columns, use the Node Finder to find a particular node or select an assignment group, both discussed next. For the type of assignment, select one from the pop-up menu in the Assignment Name column, then set a value in the Value column. Depending on the type of assignment, a value may need to be typed in or selected from a pop-up list. Use the Node Finder to locate design nodes and apply assignments to them. The Node Finder is used throughout the Intel Quartus Prime software as the main way to find and select nodes. You can use the selections in the Filter pop-up menu to filter results specifically for the current tool or situation. Type the name of a node or use wildcards in the name field to search for specific nodes. You can also select which level of the hierarchy to search. After setting up your search criteria, click the List button. Nodes matching your criteria are displayed in the list on the left. Enabling the hierarchy view, as shown here, lists the found nodes as they appear in the design hierarchy, similar to the Project Navigator's hierarchy view. Use the arrow buttons to move nodes to the selected node list on the right, and click OK to select the nodes. When creating assignments with the Assignment Editor, the QSF file, where the assignments will eventually be stored, is not updated automatically as soon as you enter the constraint. The QSF file is only updated when any of the listed events occurs. The reason for this is if the QSF file was saved every time you created an assignment. The Intel Quartus Prime software will be constantly accessing the disk and updating assignments whenever a change is made in the software. You can, however, change this behavior to update assignments immediately by going to the Intel Quartus Prime software options as indicated here. Again, this will slightly impact software performance because the Intel Quartus Prime software will be accessing the QSF file more often to save the assignments you create. We explored a variety of design entry methods and learned about settings and assignments for the Intel Quartus Prime Pro software. Intel provides multiple avenues in which to learn about Intel FPGA products. There is the Intel FPGA YouTube channel, which contains 5 minutes quick videos along with longer, more in-depth training videos. There is the Intel FPGA training website, where you can access e-learning courses made up of narrated slides presented in an interactive player, some courses with labs and demos. Lastly, you can also enroll in a live, instructor-led course presented either in person at an office local to you or virtually over the web. All instructor-led courses have hands-on labs exercises to practice the concepts you learn. If you need more assistance, Intel FPGA provides many self-help resources for you to access. For example, there are web pages, called landing pages, dedicated to specific FPGA technology like and high-speed interfaces. You can also view and post questions to the community forum, which is monitored by skilled Intel FPGA applications engineers. The Intel FPGA training team is always looking to improve our material and welcome any feedback you may have. Please email fpgatraining@intel.com with any of your thoughts or comments. Thank you for listening to Part 2 of the series, Intel Quartus Software Design Entry. Check out our other 5 parts in this learning series.